Welcome students once again into the class of topology, and now we'll move ahead where we have left last time the chapter of nets. So let us first of all start with cluster points. What is a cluster point? How many cluster points a net can have, and properties of cluster points related to nets, if the space is housed off or not, and so on. So first of all, what is a cluster point? Let there be a net. Let there be a net f x d greater than or equal to, as you have know the basic notation for a net. So let there be a net f x d greater than or equal to a point x naught belonging to x is said to be a cluster point of this net f, in short you can say. So this is a cluster point of f if f is frequently in every neighborhood of the point x naught. So that means if you are having a neighborhood n of x naught, let n be a neighborhood of the point x naught, then f must be frequently in this neighborhood n. That means for every n belonging to the set of natural numbers, there must exist some m greater than or equal to n such that your fm belongs to n. And it should be true for every neighborhood. This neighborhood n is arbitrary. You can take any neighborhood n of x naught, and then the net f must be frequently in n. If this condition is satisfied, then we'll say that x naught is a cluster point of this net. Now, let us move ahead. How many cluster points a net can have? So a net can have no cluster point. It can have a finite number of cluster points, and even it can have an infinite number of cluster points. So we'll give all types of examples. So let us first start with this particular net. Let fxd greater than or equal to, you can take this d as n, this x also as n, then define the net f n greater than or equal to. Let this be a net defined as f of n is equal to n for every n belonging to n. Now look that this net now has no cluster point. Why? Let us prove that no natural number is a cluster point of this net. You take any natural number. So let a belongs to n be an arbitrary member of n, or you can say an arbitrary natural number, be an arbitrary natural number, and we will show that this a is not a cluster point of the net. And since a is arbitrary, if a is not a cluster point, that means no natural number is a cluster point of this set. Not only natural number, you can take any real number here. So no real number is a cluster point of this net. How it can be proved? So here this a is an arbitrary natural number. If the net has this point A as a cluster point, then F must be in every neighborhood of this point. So let us take some particular neighborhood. So consider the neighborhood A minus 1, A plus 1 of the point A. I have taken a particular neighborhood, and since if A is a cluster point of F, then F must be frequently in every neighborhood. Since F is frequently in every neighborhood, then F must also be frequently in this neighborhood. And we will show that F is not frequently in this neighborhood. Your definition of frequently says that for every n belonging to n, there exists some m greater than or equal to n, such that your f of m, or you can say fm, belongs to n. This is the definition. So just take your n as a plus 2. Take this natural number a plus 2. So there must exist some m belong greater than or equal to n. That means m is greater than or equal to a plus 2, such that f of m belongs to n. What is f of m? F of m by definition, f of n is n, so f of m is m. So m belongs to n. And what is your n? Your n is this a minus 1, a plus 1. And this is a contradiction. Why? Because m is greater than or equal to a plus 2. A number which is greater than or equal to a plus 2 cannot be in this interval a minus 1, a plus 1. You can see it diagrammatically. Here it is a. This is your interval a minus 1, a plus 1. Here it is a plus 2. And your m is greater than or equal to a plus 2. So your m is on this side. And if m is on this side, how m can be in this interval? It is not possible. So that means what you have considered that A is a cluster point of this net is not true. So there is no cluster point. Since A is arbitrary and A is not a cluster point, that means no point is a cluster point of this net. So there you are having an example of a net having no cluster point. Let us have another example in which there will be, you can say one, I can give example with 2 cluster points, I can give example with 3 cluster points. So let us have an example with 1 cluster point. So define this net F from n to n as f of n is 1 if n is even, and n if n is odd. So here you are having 1 cluster point, and that is 1. Why? Because for this one you take any neighborhood. Any neighborhood means 1 minus epsilon, 1 plus epsilon. It is a arbitrary neighborhood of the point 1. Now what the definition of cluster point says that this one is a cluster point if for every n belonging to n there exists m belonging to n such that m is greater than or equal to n, and f of m belongs to that neighborhood, and that neighborhood we are taking here 1 minus epsilon, 1 plus epsilon. So this should be true for every n. This should be true for every n. So what we have to do? Take any neighborhood, any natural number n, and this m, because we want our m to be greater than or equal to n, so you just take 2n. So you know that there exists 2n belonging to n such that your 2n is greater than or equal to n. That's very much obvious because n is a natural number, it is positive. And f of 2n. What is f of 2n? Since 2n is an even number, and for even number the image of the net is 1. So this is your 1. And now it is very clear that it is true. For every n belonging to the set of natural numbers, there exists 2n, which is greater than or equal to n, and 1 belongs to this interval 1 minus 1, 1 plus 1, 1 minus epsilon, 1 plus 1, epsilon. So that means this 1 is a cluster point of this net. So this is a net having only one cluster point, unique cluster point. And one more thing is clear, that if a net is having only one cluster point, that means unique cluster point, the net need not be convergent. This net is not a convergent net. This is not a convergent because the net is frequently in the neighborhood of 1, but f is not eventually in every neighborhood of 1. So this 1 is not a point of convergence. This is only a point of you can say cluster point. This is only a cluster point. This is not a point of convergence. So here you are having an example of a net having a unique cluster point which is not convergent. So sometimes there may be a question in your question paper that can a net having a unique cluster point is necessarily convergent? The answer will be no. And here will be the example. This will be the example that this net is having only one cluster point, yet the net is not a convergent net. So this is an example of a net having one cluster point. Earlier I gave you an example of a net having no cluster point. Now the question is, can there be infinitely many cluster points? Yes, it is possible. How it is possible? So define once again a net f from n to n, and this time you define net in a different way. Actually, what the images of this net will be: f1, f2, f3, f4, f5, f6, f7, f8, and so on and so on. What you have to do, define your f1 as 1. f1 means f of 1. So f of 1 is 1. Then for next two elements, f2 and f3, you define your images as 1 and 2. For the next three elements, for the next three members, you define f4 as 1, f5 as 2, f6 as 3. For the next four, now take the group of next four members of this images of the net and define them as 1, 2, 3, 4. And then take a group of next five members, 1, 2, 3, 4, 5, and so on. So what we are doing, every time we are including one more rational number. We are starting with 1 only. Then we included 2, 1 and 2. Then we included 3, 1, 2 and 3. Then we included 4, 1, 2, 3 and 4. And then we included 5, 1, 2, 3, 4 and 5. Next time we will include 6, next time we will include 7 and so on. So this is the net. And for this net, every natural number is a cluster point. Because suppose you are taking 8. 8 is a natural number. And we will prove that 8 is a cluster point. 8, I am taking an arbitrary member of the set of natural numbers. You can take 7, you can take 10, you can take 1000, any natural number you can have. And let us see whether this number is a cluster point of this net or not. So how to check? For every n belonging to n, there should exist some m greater than or equal to n such that f of m belongs to the neighborhood of this point. Neighborhood of this point is 8 minus epsilon, 8 plus epsilon in general. And look now, this one is in the starting. After that, there are so many 1, 1, 1, 1, 1, 1. So there are infinitely many ones in this, the set of images of this net. There are infinitely many 2s, 2, 2, 2, 2, and so on. There are infinitely many 3s, 3, 3, 3, and infinitely many will be there. Similarly, every natural number will exist here in this set of images infinitely many times. So 8 is also a natural number. So 8 will again be in the set of in the 8th set. You will have first time the number 8, and then you will have 8 in every following set. In the 9th set, in the 10th set, in the 11th set, in the 12th set, in every subsequent set you will have 8 as a member. So whatever the natural number you will take, you take m to be greater than n from the next set. Suppose you are taking n from the pth set. Take m greater than or equal to n from the p plus 1th set. Since pth set is containing your m, p plus 1, p plus 2, p plus 3, every next set will contain this m, and so therefore m fm in this case will be 8. So it is belonging to 8 minus epsilon h plus epsilon. Here fm will be 8. You taking from the 8th set, then you take m from the 9th set, you can take m from the 10th set, you can take m from the 11th set, you can take m from the 12th set. In the every set that is subsequent to the 8th set, you take m and your fm will be 8, and that will belong to 8 minus epsilon h plus epsilon. So there will be one particular m in every subsequent set whose image will be 8. So similarly you can say this is true. And this 8 I have taken any natural number. It is arbitrary. So that means every natural number is a cluster point. So how many cluster points can a net have? It can be infinitely many. In the first example, you have seen there are no cluster point. In the second example, there was one. In this example, there are infinitely many cluster points of this net. So, number of cluster points can be any. And one more thing what you have learned in this video is that if a net is having a unique cluster point, it is not necessary that the net is convergent. It may not be convergent, which we have seen in the second example. So, I am closing this video here. In the next video, we will have more and more properties of cluster points of a net. Thank you. Thank you again.